Hey everyone. So today I'm going to be designing a location or proximity service, a location service or something like Yelp. Essentially, what you do at Yelp is you look for pretty much restaurants nearby and it tells you restaurants that are in some sort of radius around you. So that's why it could also be called location based or proximity service. I've seen it flipped in multiple different ways, but let's just stick to designing Yelp here and you'll see why location matters here. I mean, I'm sure everyone has used Yelp. So start practicing. So your task is to design a business review and recommendation service similar to Yelp. So, what are the functional requirements of our system? The functional requirements are users should be able to search for businesses by name, location, latitude and longitude, and category. So, they should be able to search simply by name and then also by locations that are nearby to some radius and then category. And users should be able to view businesses and also view their reviews. And then users should be able to leave reviews on businesses with a rating from 1 to 5 and some optional text. So that's what our system needs to do. And the scale of our system is pretty big, which is 100 million daily active users. And we're going to have 10 million businesses on the platform. Also, one of the functional requirements we have to hit is users can only leave one review per business. So a lot of times in these system design interviews, you need to make sure you hit all of the functional requirements. That's sort of table stakes for actually passing the interview. And then non-functional requirements, depending on your seniority, we'll get to we'll pass. Like if you're a junior candidate, if you hit all the functional, I'm sure you'll get the job. Mid, if you hit some of the if you hit the functional but don't hit any of the non-functional, you probably won't get the job. So definitely, we're gonna dive into some non-functional requirements as well, but make sure to at least hit the functional requirements. So this is the delivery framework that Hello Interview likes to give, and I've seen it different across different platforms. And if you read Alex Zhu's system design book, this one I have right here, the delivery framework is a bit different. So, but the way that they like to do it is they do requirements gathering. They talk about the different core entities. This is the data model. Then they talk about the API. So all the different APIs that we expose to our clients that they can hit in order to interact with our service. And then we start getting into building all the boxes and things of like how the data flows within our system and the high level design of everything. And then after that, once we have our system, we look at it holistically. We start diving deeper into some of the different parts. So some of the deep dives here will probably involve things around proximity service and how to make sure that happens fast. So let's just hop straight into the first part, which is figuring out what the non-functional requirements are. Okay. So what are the non-functional requirements? So I start to think right away about the CAP theorem. So users should be able to search for businesses by name, location, and category. So I think with our system here, we probably care more about availability over consistency. We want to make sure our system is available to our customers as much pretty much all the time. We don't want our system to go down. And if we need to sacrifice users seeing inconsistent view for very short periods of time, that's fine. It's not like a banking system, or it's not like Ticketmaster or any of those ones where consistency is very important because you don't want to double book. You don't want someone. You essentially don't want to double book. Yeah. So there's nothing we need to really care about that. So let's just make sure our system is available as much as possible. So it's a good user experience. So say we'll prefer availability over consistency. We want our system to function all the time, and will trade off um, delays in clients receiving updates. So our system will be eventually consistent. Our system will be eventually consistent. So the way I do it is I kind of look at the functional requirements and start figuring out what are the non-functional requirements that might come up based on our specific use case and system here. So users should be able to view businesses and their reviews. I also with the search, I think users should be able to search for businesses by name, location. I think the search needs to be fast as well. So there could be so many. If you're living in a city, there could be so many. There could be tons of restaurants there. So you want to be able to search for it really fast. And yeah, this is going to be really important because you could easily build the system, but it could be really slow. So we'll probably get into that in the deep dives. But let's just say low latency when it comes to search. And let's just put a number on it. Probably, let's just say 400 milliseconds search. This is kind of arbitrary. I think 200 milliseconds is really fast. That's almost real time. So we just doubled it. We could say like 500, 600 here. I think it's kind of arbitrary. Obviously, you don't want it more than 1 second. So let's just say 400 milliseconds. But you could probably do some more deeper calculations here. You just should be able to leave reviews on businesses. So yeah, I think that's kind of all of our what we need here, and we probably just need some just be able to handle scale, obviously, because we have 100 million daily users and 10 million businesses. Daily users and 10 million businesses. So this kind of, so we just want to make our system highly available, make the search really fast, and then handle a large amount of scale. So probably do some horizontal scaling or something like that. But let's see if that captures all the non-functional requirements that they're asking us to figure out. Cool. Nice. So we correctly identified the need for low latency in search operations, which is crucial for user satisfaction. This is also important for user satisfaction, which is just making sure our system is highly available. You don't want them searching for restaurants and they can't find it. And then you also recognize the importance of eventual consistency for reviews, prioritizing availability, which is a smart trade-off in this context. So let's see what they said. Okay, so yeah, they said the same thing of availability over consistency, and eventual consistency is fine for reviews. Low latency, they're saying under 500 milliseconds, and then yeah, also scalable. I'm pretty sure the scalable part we don't really need to say. I mean, every system kind of needs to be scalable, but I guess I'm just going to start repeating that every time. Okay, what are the next part? What are the different core entities of our system? So to figure out the core entities, I start looking at the functional requirements, and then I just start to think, what do I need to build, or what do we need to store in our database to satisfy these functional requirements? So let's just get into right here. Users should be able to search for businesses. So of course we're gonna have users that probably store login details and things like that, and we'll probably have businesses. So these are the different businesses that we're searching for in our system. They'll have all these different categories like latitude, longitude, and category. But after that, we have our businesses, and then we're also going to have reviews that are tied to those businesses. And I think Hello Interview gives this advice all the time. And honestly, what I like to do is type out all the core entities and type out all of the different columns that are going to be here. So I'll just say, okay, users is going to have a user ID, business is going to have a business ID, reviews is going to have a review ID and probably a foreign key to a business ID. So I usually start to list those out, but they said in the core entities, since you probably don't know, maybe just list them out now. So I'm going to try that out and just see how it goes. So I'll just get the feedback. Hopefully we hit all the core entities there. Nice. So we have the users. Nice. Literally have the exact same one as us. Okay, let's start thinking about API endpoints. So again, we have to start thinking about our functional requirements here, and then we have to start figuring out what API endpoints does the client need to call in order to satisfy these requirements. And I'm just gonna do very basic HTTP endpoints just because that's what I'm very used to, and it's kind of a easy format to go with. So users should be able to view businesses. Am I allowed to move this thing? I like how it's positioned here now, but essentially, okay, what are we gonna do? We're gonna do. So what are different users should be able to search for businesses by name and location. So I think what I noticed is we're probably not dealing on the business side. We're not talking about how businesses are able to make updates and stuff. We're kind of assuming that the business data is already in our business database and we're just querying against it. So let's look at the first functional requirement. Users should be able to search for businesses by name. So let's do get, and we get against our resource businesses, and there's gonna be query parameters here, but description would be like search for businesses by name, location, category. And we're gonna have query parameters usually with a get request. That's how you perform different filters. Query params. We're gonna do name string. We're gonna do location, or we're gonna do latitude. So probably some integer, longitude. Probably some integer as well. Maybe a category. Could be like some enum or string. But then we're also going to have probably paginated because it's going to be a large list. So probably like a limit and offset. This is for pagination. These are usually integers. And those are for pagination. And this is very naive pagination. And there's other ways like cursor-based pagination. But for an interview, I'll probably just mention that, and just to simplify it, let's just say limit and offset for now, so we don't have to really, because that's like the very simple way of paginating. So that's how we're gonna get our businesses. That'll be able to, once we hit that endpoint, it's gonna do that search based on based on what they passed in as query parameters to this endpoint, and then it should return back a list of businesses, right? And when they probably click into one of the businesses is when they start to see the reviews for businesses or for businesses. But let's do that. Get business. Users should be able to view business and their reviews. So maybe let's go. We can get businesses, and we could say business. We can have a different path parameter here, business ID, and then this will return back one business right here, and maybe. Let's see. Maybe do we want another endpoint to get back? Let's probably to separate concerns. Let's make another endpoint for grabbing the reviews. So let's see. Gets metadata about business. No query parameters here. The path parameter. Path param is business ID, and we say the path parameter, we have a business ID, and yeah, that's just the ID, the business. Simple as that. So now we get business ID. Let's get reviews for a business ID, and it will return us a list of reviews. And then let's just add in paginations here as well. We want to make sure those are paginated. So that's how we get all the different reviews. And we should able to leave reviews. So let's just say we have another post request. Post reviews, business ID, and then we're gonna probably return back a review here, and yeah, creates a. So this one, post reviews, creates a review for a specific business. Probably in the headers we have our authentication. Auth token or whatever we're doing for authentication. Query parameters when we post. We're just gonna have a body, and this is we're gonna have all the things. Body is gonna be everything related to the review, like the review and how many stars we're giving. So does that hit all my functional requirements? So users should be able to search for businesses by name. That's this first one. Users should be able to view businesses and their reviews. That's these two endpoints, being able to get the business and then also getting the reviews from the business. And then after, users should be able to leave reviews on businesses. That's this post request. So I think that hits all of our functional requirements there. And let's just like get feedback on that now. Let's go. So you provided a comprehensive API endpoints covering all the core functionalities, including search, business, details, retrieval. We follow RESTful principles with clear separation of concerns and appropriate HTTP methods. You included paginated parameters for the reviews, which is essential for handling large. Okay, adding pagination to the get businesses. Didn't I do that? In the clearly defined the. Okay. Okay. Consider it more. Okay, get business. Okay, let's view their answer. Wow, there's way simpler. Just searching. They're able to view. They get businesses also return review, but there's no pagination there. And there's review. You can actually post a review. I don't know. I like mine because we could actually paginate getting the reviews. Because what if there's a ton of reviews? Cool. Let's move on to the next. How will users be able to search for businesses? Okay. This is gonna be, now we just got to start drawing some bounding boxes and stuff. Let's see. We're gonna have our client. So what they're gonna do is they're gonna interact with an app server. App server is any server just gonna respond to client requests. This could be like a Django server, an Express server, any of your regular servers hosted maybe like on an EC2 instance or however you like to host your servers. Then finally, we'll have our database, right? So how will users be able to search for businesses? Pretty much when they hit the app server, they're gonna make a post request, or they're gonna make that get request to our app server, and the app server is gonna parse out everything related to that query, or build the query based on what was passing the query parameters, query the database to get all of the businesses that are relevant, and then return that back to the client. That's a very naive approach because it's going to add a lot of load to our database. We need to actually improve that. And we're not really talking about how we're structuring our database just yet. So the database might be slow. So let me just think if this is okay to just do. because maybe in the deep dives we'll get into it. So let's just say how will users be able to search when client makes a GET request to app server. When the client makes a GET request to the app server, app server parses out the query params to build the query. App server queries the database. So app server queries the database, and after the app server queries the database to obtain results, app server returns results to the client. This is a note. This is a naive approach. There is a lot of load on the database, and we don't talk at all about how we make the query efficient, right? Because there's multiple ways to make the query efficient, and the biggest one is using geospatial indexing or geohashing to easily figure out, like, if they look at the latitude and longitude, using geohashing to find just nearby businesses, and I'll explain that after. But yeah, pretty much this is the naive approach. Let's see if that works. Oh shoot, I have to explain it to them. And then we'll like get more into it in the deep dive. But so how will the users be able to search for businesses? Essentially, the user will use a GET request to the app server, and pretty much in the GET request, they're gonna specify all the query parameters that they're looking for. Maybe it's by latitude and longitude, maybe it's by category, maybe it's by name, or maybe it's a combination of those different ones. But essentially, once they send the GET request to the app server parses out the GET request to form its query that it will eventually create a database with and obtain the results. Once the app server queries the database and obtains results, it's going to send those results back to the client. So that's kind of the flow. But it's a very naive approach. There's a lot of load on a database, and we don't talk at all about how we're going to make the query efficient, because there's lots of parts that we can make efficient. Like, how do we grab things in a radius, or like locations within that radius really fast, using a traditional database isn't really that fast. Why did it stop? Like, using a traditional database isn't really that fast, even if you index based on longitude and latitude. But yeah, that I'll explain that more. Maybe we could talk about a deep dive, but this is a very simple high level design. See how it reacts. Did my Wi-Fi go out? Okay, get feedback. Dude, my Wi-Fi went out. Refresh this. My Wi-Fi went out. Dude, my Wi-Fi is terrible. It's crazy. And I pay $100 a month for this Wi-Fi. Let's go. So you provide a clear and concise high-level design that effectively addresses the requirement of how users will search for businesses. Your explanation aligns well with your whiteboard diagram, demonstrating a good understanding of the flow from the client request to database query and back. You acknowledge the simplicity of design and mention potential areas for improvement, showing like there are scalability concerns. So consider discussing potential optimizations for database queries such as indexing strategies or caching mechanisms to improve search. You may want to explore more scalable solutions for future iterations, such as implementing a dedicated service. It would be beneficial to mention how you'd handle error cases or invalid search parameters in your design. Yeah, that makes sense. See how they did it. I think they just did a very simple thing too. When a user searches a search criteria like business name, category, or location into a client app, it sends a GET request to our API gateway. The gateway routes this request to the search service. The search service then queries the database with where clauses matching the user's input criteria, searching through business names, categories, and locations. So yeah, essentially what I'm doing, same thing. Once the search client retrieves it returns data. Yeah, this is exactly what I did. So let's just move on. How will users be able to view businesses? So I think yeah. So pretty much our system right now handles that. So after the client is able to receive a list of results from the server, it now has a list of business IDs, and it essentially doesn't have we don't return like a big list of um, businesses with all the metadata right away. We just really return the IDs to the client and just enough to show them maybe whatever view that they need to see. So pretend if they have a list of restaurants with like with a small thumbnail of what the restaurant is and maybe a small thumbnail of the stars. But essentially, when they click into a specific business, we're gonna hit our other endpoint called get business, which will return us all the details about that specific business, and then it'll also also subsequently call a request, the get request to get all reviews for the business, and it'll probably just load the first page of results. So we don't have to load too much reviews at once. Maybe 50 reviews is good. But essentially, we can use the same client app server database high level design we have right there. But yeah, that's kind of how the data flow would work. Let's see how I do. Let's go. Okay, cool. Whatever. When a user wants to view details, the client sends a GET request with a business ID to our API gateway. Yeah. Okay. Cool. Pretty much the same thing I mentioned. Let's move on to the next part. Reason through this one. How will users be able to leave reviews on businesses? I mean, we're gonna keep going with the same exact um, same exact high level architecture here. So let's see how we users be able to view, and then I'm gonna scale this up hard during the deep dive. Okay, let's get into it. How will users be able to review, or leave reviews on businesses? Essentially, clients will use our post request or our post endpoint, so they'll be able to post reviews for a specific business ID. So we have that API for posting reviews, and if you pass in the business ID, we'll be able to create a review for that specific business ID you passed in. Yeah, you'll probably pass in a header which has your authentication. So this could be a session ID or JWT. Let's just call it an auth token. So the backend could authenticate you, and yeah, once it authenticates you, it's gonna see if you already left a review. If you didn't already leave a review, it's gonna leave a review, or it's gonna insert a review into the database for you. And what it's gonna also do is, or how it's going to populate what's in that row in the database that it creates is based on the body that you pass into your into the post request. So you pass in all the details into the body, pretty much like the star, how many stars you want to rate, um, also the feedback you want to give, and yeah, we're gonna create a row there based on that data, and then we're gonna return back that specific. Once we create that entry, we'll probably return that back to the client, so maybe they can update their view to show that they left the reviews, kind of like an act, and yeah, they could also refresh the UI when that happens to show that person's review right there right away. Otherwise, people will think that their review just disappeared out of nowhere. This is fun. I like these product focused ones. Let's go. Offer letter incoming. See how they did it. So they have a review service. They love to do this microservice architecture. Would make sense. So this request user ID. The gateway routes this to a review service. The review creates a new entry in our database, associating it with both the business and the user. Yeah, same thing. Are we finally in our deep dives? Okay, this is the fun part, our deep dives. How would... Okay, I'm gonna take a quick break and we're gonna get right into our deep dives. Okay, let's get straight into the deep dives. How would you efficiently calculate and update the average rating for a business to ensure it's readily available in search results and still accurate? That's a good question. How do we calculate and update the average rating? So the most naive way for this is probably just when we would query the whole database for the reviews, and then we figure out pretty much we query the whole database for the reviews, and yeah, once we figure out the reviews, we sum up all of the stars and then divide that by pretty much how many reviews there were. So yeah, that's how we would get the average rating there. But obviously, if everyone's asking for the average rating, we're going to have to be querying the database like crazy. So what we can do is we can probably build a caching layer on this. So what we can do is as reviews come in, and like we probably want to cache that. So let's just say so what we can do is build an in-memory cache, use a Redis cache. So we'll have a Redis cache, and what's going to be in this Redis cache is pretty much going to be a hash map of different business IDs, and let's have some of stars and reviews, right? It's gonna be pretty much a hash map of that. So pretty much to calculate the average rating, we just take the sum of stars divided by the number of reviews, and pretty much as reviews come in, they'll update the cache here. I think that would be like a nice simple in-memory solution. But we still write to the database, so if we ever need to rebuild the cache, we can. And that will give us search results, and it's still it's gonna be like accurate as soon as things come in. Yeah. Let's just write that down, or maybe I'll just explain it. So I'll explain it back to this AI real quick. So yeah, to efficiently calculate and update the average rating for a business, the very first naive approach would be every time we want to calculate the rating, we could query the database for all of the reviews for a specific business, and sum up all of the stars and then divide it by the count of reviews. But that's going to be very inefficient because everybody will have to query all the reviews for a specific business every time they want to see the average rating. So to avoid that much load on our database for doing that many queries, we can make a Redis cache. So a Redis will be an in-memory store. We'll basically store an in-memory hash map where the hash map has a key for a business ID, and then the value will be the sum of stars and the number of reviews. And this is going to be we'll essentially first every time a review comes in, it's going to store that review in the database, but then it will also update the cache and then return back to client, and it could probably update the cache asynchronously. But let's just say it does it synchronously where it updates the cache, so it's pretty fast. It pretty much accesses the business ID using the hash map, and it increases the sum of stars and the reviews. So now whenever we need to figure out the number of stars for a specific business, we could just look in the Redis cache, and if it's not there, then we calculate it using the database. But yeah, that's pretty much how we'll handle that. And yeah, we don't really need to handle race conditions because Redis is single threaded, but that's the way that we'll able to handle our search results really fast, and they'll be pretty accurate, I think. What? Did it not? Was it not able to get? Uh-oh. Okay. Now I need to explain that all over again to it. Testing, testing, testing. Is it not getting my audio? Fix my sound. Testing, 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 testing. Cool. Reset. So, to efficiently calculate and update the average rating for a business, what we're going to do is we're going to create a Redis cache that has a key for a business ID, and the value is going to be a tuple of the total number of stars and the reviews. That's going to easily allow us to get the average rating. And yeah, that will reduce the load on our database and make the calculations of averages pretty fast. It's pretty much all one operation, and since it's in memory, it's gonna load it up really fast. It doesn't have to scan through the table. Yeah, that's pretty much what we're gonna do. Every time a review gets posted, we're going to update the database because we still need to persistently store this data in our database so we can rebuild the cache whenever the cache goes down. But we'll store it in our database, but at the same time we'll update our cache. So we'll basically write to the business ID. We'll increase the sum of stars based on the number of stars that were given and increase the number of reviews by 1. And yeah, that will allow us to actually calculate the average rating pretty fast. And pretty much if a client ever requests the rating for a business, it could just look in the Redis cache and figure out the average rating there. And it's going to be pretty accurate up to the minute because we're pretty much updating the Redis cache as we go. If it's not there, then we can create a database and build that entry in the Redis cache. But that's how I'm thinking of doing it. I had to slim that down a little bit because I already repeated myself multiple times. Let's go, please. See if the Redis cache is good. Didn't get the full stars. Okay. I see. You propose a Redis cache, which is a good approach for reducing database load. Usually includes updating both the database. Yeah, there's like a data consistency issue now because now our database needs to be consistent with Redis cache. So I see what the concern is there. Let's view the sample answer. We'll add average ratings, a num ratings, and a version number to our business table. When a user submits a review, our reviews needs to perform two operations atomically, adding the new rating and updating the average rating. We need to use a transaction with either row level locking or optimistic concurrency to ensure consistency. Without this, if two users submit reviews simultaneously, we would lose one of the updates or end up with an incorrect average. So using optimistic concurrency control, we fetch the current business data, calculate the new average, and attempt to update. Okay. Yeah, I see. They're just storing a new in the business. They're deduplicating the data essentially or denormalizing. Um, yeah, let me look up. Did I say that right? Denormalizing. Denormalizing data is, or I think they're normalizing the data. I don't even know. It's one of those two. I need to look it up. But they're essentially storing a copy of, or they're instead of just deriving it from here, they're just storing it there to make it faster. But yeah, that kind of makes sense. I like their approach too, of just using optimistic concurrency, so they don't have to deal with a cache. Yeah, that's true. I see. Yeah. Next question. Whatever. How would you modify your system to ensure that a user can only leave one review per business? To our system, if we're using a SQL database, I guess I didn't talk about this before, but we'll probably use a SQL database for this, like Postgres, just so we can easily handle some of the consistency related things. And since this is not going to be like a high volume application, I think a database like Postgres is good enough here. And what we're essentially going to do is we're going to be able to enforce constraints on the database. So, I mean, if we could use NoSQL for this as well, but pretty much reviews, we can make reviews, put a unique key based on the business and the user ID. So that way, that would be a primary key, like a composite primary key. That way, if they try to insert the same user ID for a business ID, like business ID, user ID combo, that's automatically going to throw an error at the database layer. And yeah, we'll just have validations against that to not allow them to insert two. Yeah, pretty much using database constraints and database level checking. But we could also do it on the application layer as well, like quickly query if that already exists. And if not, just don't insert and return a user. That will allow us to not let the database like give us the error. But yeah, either on the app level or the database level, maybe on both. Let me think. But yeah, that's kind of how we could allow users to only review one per business. Get some feedback. I get lazy with this. I stop even writing. Nice. So consider. Okay, let's see what they said. We can leverage Postgres' ability to create composite primary keys. We'll define our reviews table with a primary key constraint on both the business ID and the user ID columns. This way, database itself will enforce the uniqueness. Cool. When we try to insert a new review, if a record with the same business ID and user ID already exists, Postgres will throw a unique constraint violation. Our application catch this and handle it appropriately, maybe by updating the existing review instead of creating a new one. This approach is robust because it enforces the constraint at the database level. That's what I was saying initially, but we could do it at both, but database levels is our most reliable. So even if we add a new service or have multiple application servers, they all interact with the same database, so this rule is always enforced. It's also efficient since the database can optimize for this type of lookup. Cool. There's tons of answers. They liked my answer there, so let's move on. How can you improve search to handle complex queries more efficiently? Searching for a business with various criteria like Italian restaurants near me can be... How do you optimize the search functionality to ensure low latency for complex queries that include location, radius. Man, this is a lot. I wish they broke this up into, okay, how do we make location faster? How do we make um, searching by name faster or category? Let's see what this next one. How do you modify? Okay. Um, let's just like look at this and start breaking this down deeper. Because the different operations, it kind of depends. There's multiple things we can do here. So for searching by term, we can use, so by searching by term and category, we include location. We can use, for searching by term / category, we can use Elasticsearch to create an index, reverse index of our data. Will, like, the keys of the index will be the keys will be search terms and category, and values would be business IDs. So if we search by a specific term, we can be able to figure out all of the business IDs related to that specific term if when we create this sort of reverse index. Would be, and then that's what Elasticsearch will return to us, and then we can then query for those specific business IDs. But yeah, that it'll be sort of reverse index, and Elasticsearch also allows us to do like full text. Elasticsearch also has fast full text, like full text queries, has support. So yeah, we just kind of build that reverse index of maybe different terms, categories, or sentences, and then map those to business IDs, kind of thing. For location and radius, we can use geohashing. So we can use geohashing in order to figure out all of the closest businesses. So given a longitude or latitude and longitude, we could figure out a geohash and then just query the 8 neighbors of that geohash if we do. And I could, this is like a whole video in its own geohashing, but essentially what you could do is break down the world into some sort of grid. I could probably do a video on this as well, but giving some sort of latitude and longitude, it'll give you a certain area in the grid, and then I could grab all my neighbors around it, and that will give me all the businesses in the specific radius. And yeah, with geohashing, you can make these squares smaller or bigger. One thing that's one way we can use geohashing here, or we could use something like a quad tree, because quad trees are kind of good for, are better actually for businesses, because if there's really dense locations for businesses, like geohashing is more just like predefined squares. So if you have hotspots, there's going to be tons in one specific tile, but quad trees will break those down further. And yeah, so we could use geohashing or quad trees to find out. And you can see this is already going over 50 minutes. Usually system design's over an hour. So you probably won't get deep into this, but just mention that you can use geohashing or quad trees to find, basically find businesses nearby. Cool. So how can we improve? Oh, sorry. Let's just say let's just say there's gonna be a search service. I'm gonna start breaking these down further. I noticed a lot of times I'll just make this one app server handle all this work, but I'm gonna have like a search service, and maybe they can talk directly to the search service when they're trying to search, and the search service has access to Elasticsearch index, or this is Elasticsearch. And there's so much different things that we need to maintain for like maintaining consistency between our database and our Elasticsearch, but that's like probably like we could dive into that a lot of how to uh, maintain consistency between these two data stores. But I mean, I don't think this question wants us to go that deep right now, especially in the span of the interview. But maybe we could talk about it at a high level. Let's see. Let me just give my response here. So, how can we improve the search to handle complex queries more efficiently? So, I think it all depends on the type of search that they want to do. If they want to search by location or radius, the best way to do that is through geohashing or using quad trees. That'll allow us to find businesses that are nearby based on proximity. And yeah, that just allows us to really query by location a lot faster than if we were to just use a traditional SQL database. Because yeah, SQL database, our queries, even if we index, will just it will just be too much data that's going to come back in those queries, because we essentially have to range look up the latitude. So it's going to like pretty much give us like that whole column, and then range look up the longitude. And I think longitude is horizontal, and that's going to pretty much give us a range of restaurants across the whole like line across the world. It's going to kind of like give us something like we'd have to search by latitude by like all of these tiles, and then all of these tiles. And you could, if that was the world, that would be a lot of different queries or results. So yeah, kind of that we'd use for location radius. We can use geohashing or quad trees. If we want to search by term or category, we can use Elasticsearch to build a reverse index on our data. The keys of the index will be different search terms and categories, and they'll map back to business IDs. So that'll allow us to easily search back, look in terms of different terms or different categories, and return us a list of business IDs that match, and we'll leverage Elasticsearch for that. And Elasticsearch also has support for full text searches. So yeah, that's how we do that. And yeah, we'll introduce another search service that will interact with Elasticsearch. Yeah, that's kind of how we'll handle that complicated. And how what would we probably want to talk about is how do we maintain consistency between our database and our Elasticsearch index. So what we're going to do is, as we write to our database, maybe we'll also write to some queue, some Redis queue, and we have like producers, or we'll write to some Redis queue or some queue that, or like some change data capture that will essentially look at all the changes happening in our database, and then update our Elasticsearch database based on the changes happening in our database asynchronously. So as changes come in, we just put it in the queue, and eventually it'll update our Elasticsearch index to match what's in the database. So that's how we'll handle keeping those consistent. But yeah, they can sort of drift. So we'll eventually just yeah, there might be a little bit of drift, but I'm actually not sure how to handle that. So maybe I'll look into after this video. Holy, this is a grind. Oh, I didn't say Elasticsearch for geospatial. Let's see what they say. So they're using Elasticsearch as well. So they'll use an inverted index for full text search. We'll look at that in a second. But yeah, since this is, let's try to handle this last one. How would you modify your system to allow searching for predefined location names? Yeah, I think what we can do here is also leverage our Elasticsearch index. So as businesses are being put into our system, we could parse out the latitude and longitude and then just figure out what city they're in and also maybe what neighborhood they're in. And that could be part of our reverse index or our inverted index. So yeah, pretty much based on the latitude and longitude, we're going to be able to we'll be able to define or we'll be able to figure out what neighborhood they're in, and then our Elasticsearch index will be like these are the neighborhoods that are in the mission district, and it'll have a list of business IDs. But yeah, and then the same thing with San Francisco. We kind of just leverage our inverted index and just make sure that we're able to map cities and neighborhoods to business IDs. So yeah, it's all gonna be logic that we run ourselves. When they pass in reviews, we don't expect the client to do all this work because they can get it wrong. Let's just assume that the client sort of submits their business, and then we figure out um, which neighborhood and city they're in, and do all that indexing ourselves in the back end. Let's see if we can finish this off. Then I'm gonna go read this article and see what I did wrong. This is the best way to practice. So y'all are just literally seeing how I practice this stuff. Oh my. Okay, you got. Okay, what is it saying? Location matching. First, we'll store polygonal boundaries for cities, neighborhoods, and districts in our database. These, okay, accurately represent. Okay. When a new business is added to our system, we'll determine all the polygons it falls within. This might include a city, or and perhaps a district. We'll then store the location strings with. That's what I said. For example, a business in might have location so with different tags. When a user searches, we simply match against these. Okay. I mean, that's kind of what I said. It's all good. We complete the practice. Now it's time to read the solution. But yeah, that's me practicing and designing a proximity service, designing Yelp, talking a lot about different things like geohashing. But yeah, thanks everyone for tuning in. See y'all in the next video.